Hello everybody, my name is Tyler Lay. I'm a professor at Oklahoma State University, and I'm going to be talking to you about the super air meter today. This is a topic that we've been working on at Oklahoma State for about the last 8 years, and it's been the work of a number of different graduate students who are all listed at the bottom of the page here. And so a big thanks to all of them for all their hard work, because it could not have happened without them. Also, a big thanks to the people that helped funded this research. A number of them are listed on this page. This is a part of a larger pool fund study where different state DOTs all kicked in money to help make this research possible. Here's an overview of my talk. I'm going to first talk about the big picture, then give you an introduction to air and train concrete, talk about why is the super air meter, or SAM, useful, and then back to the big picture. Here's this big picture. In my gut, in my soul, I know, and I hope you do too, that we need our infrastructure to last as long as possible with little to no maintenance. This is what we have to have as a society. We don't have the money or the resources to keep fixing it and duct taping it together. It just doesn't work that way. Hence, we need our materials to last as long as possible. And they have to do that to be relevant, to remain relevant. And if our materials cannot last as long as possible, we are going to find new materials that can do this. Ultimately, we need tools to help us achieve these goals. We need to do this economically, and we have to do it without impacting our productivity. We have to be able to still build at a very fast rate. We have to be able to do it economically, but we ultimately have to be able to hit these first two bullet items as well. We need things to be durable and long-lasting. And I'm going to be talking about freeze-thaw durability today. And the key to freeze-thaw durability is to add air to concrete. You'd say, how do you do that? Well, you add a soap or surfactant that you mix into the concrete while you're making it. And it's called air entrainment. And these bubbles are the key to the freeze-thaw resistance of concrete. And this is a big one. The second bullet item is massive. The volume of air in your concrete does not equal your freeze-thaw performance of your concrete. And you'd say, what are you talking about, Tyler? My spec book says that if I get 6% plus or minus 1.5% air or so inside my concrete, then it will be freeze-thaw durable. That's not true. That's not true at all. That was actually positively, totally true in 1952. Okay? But that's not true anymore. In 1952, we only had a single air entraining agent, or single admixture, an air entraining agent, that we use in our concrete. Our concretes today are much more complicated. But we need new tools to help us better understand this. And this is important, this last bullet item. Smaller bubbles are much more effective in providing freeze-thaw resistance and have a less of an impact on our concrete than larger bubbles. Ultimately, to provide freeze-thaw durability, we need three things. We need durable aggregates. We need a high-quality paste. And we need a high-quality air void system. Now, you get durable aggregates usually by local experience. People know the good rocks from the bad. You get high-quality paste by having a low water-to-cement ratio, including things like supplementary cementitious materials that help refine your actual concrete microstructure over time. But today's focus is all about the air void system, okay? The bubble size and spacing inside the concrete. The most challenging aspect of concrete to get right is the air content, and that's why I call this the air entrainment blues. If you look at the variables and the things that can affect the air void volume and air void quality in your concrete, the list is daunting, okay? It's just really challenging to get it right. And ladies and gentlemen, large bubbles are your enemy. Large bubbles are the reasons why people have so many problems. We've got two air void systems here. One on the left and one on the right. Both of them have the same volume of air. But the one on the left is made, that volume is one big bubble, and the one on the right is a bunch of smaller bubbles. Now, if we look at freezing and thawing, as water starts to freeze inside that gray area, that's the paste, okay? as it starts to freeze, there's only a certain distance that it can travel before it has to reach a boundary. Okay, and I've shown that here. And that distance is not dependent on the size of the bubble. It's dependent on the qualities of the paste. Anyway, the point here is that you get a lot more protection, a lot more orange zone out of air void system B than you do out of air void system A. And what's the difference? At the same volume, B is a bunch of small, well-distributed bubbles. A is that same volume of air in one big bubble. We want B for freeze-thaw durability. But also, the larger bubbles are much more buoyant. It's much easier for them to escape out of your concrete. This could be a reason why you make concrete and batch it and you measure it at the plant and you have something like 6 or 7% air and everyone's happy and they're high-fiving. And then you drive it down the road 30 minutes to a job site, you go to check it there, and you're down to like 4% air and everyone's crying, okay, and pointing fingers and fighting with one another. One of the real reasons this can happen is that the large bubbles are buoyant and they will escape out of your concrete over time, decreasing the observed air content. You say, I've never heard that before, Tyler. Well, here's some data from our lab at Oklahoma State. On the x-axis, I'm showing time, and on the y-axis, I'm showing the percentage of the original air content. What? Why are you showing me the percentage of the original air content? Why don't you just show me like 6%? Well, all of these mixes were about 6% air in the ballpark, but it's pretty challenging to get the exact same air content every single time. So what we've done instead is we've just normalized them. We've just divided by the original air content at time 0 right out of the mixer. Everything starts at 100%. And you can see the mixtures I pointed this line, the large bubbles line. Look at this. Look at this. The volume of air lost is about 50% after an hour. That means if you had 6% air in your concrete to begin with, after an hour, you would have 3% air in your concrete. And if you happen to have sampled it somewhere in the middle, you would have somewhere in the middle. But then if you look at the mixture with small bubbles, the blue line, look at this. Holds air, holds air, holds air, and then drops just a little bit. Just a little bit. Now, the mixture with large bubbles is common, is a combination of admixtures that's commonly used inside concrete today. Doesn't have to just be admixtures, it can be other things that cause it, but it has predominantly large bubbles. And the mixture with small bubbles only has a single admixture in it. And it was extremely representative of our concrete in 1952 when this type of stuff was originally investigated by Paul Klieger, the Portland Cement Association, when he established the air volumes and the procedures that we still use today to evaluate our concrete mixtures. 1952. It's a long time ago. Our concrete's changed a whole bunch since then. So why are large bubbles so bad? They leave your concrete and change the volume of your air. Nobody likes that. They don't help us with freeze-thaw durability. Nobody likes that either. And larger voids or larger bubbles will reduce your strength more than smaller bubbles. So what causes these large bubbles? Anything on this list can be a cause. Okay? Admixture incompatibility. That can cause it. If I use a group of admixtures, and some modern concrete mixtures can use up to 4 to 5 admixtures in them, if they don't play well together, just like if you're taking medicine, lots of different types of medicine in the human body, sometimes they don't play well together. Same thing here with admixture incompatibility. That can be as a cause of large bubbles. Admixture cement incompatibility. This is strange, but I've seen it. One cement, for whatever reason, has no problems with a certain group of admixtures. They change cements, okay? All of a sudden, all hell's breaking loose. Everything's going crazy. There's some kind of interactions, and we need to better understand these things. Your sand gradation. As your sand gradation gets more coarse, you will get more entrapped air inside your concrete. If you have inadequate mixing, okay, that can be a big reason why you'll have large bubbles. As your alkali content of your binder happens to change, that has an impact. The grinding aids used in the cement, the changes in temperature and pumping are all things that can have an impact on the bubble size of your concrete. You can still get a good volume of air, but the bubbles can be too large. So how do you measure this? How do you know if you've got large bubbles or small? And currently, the most established procedure is the ASTM C457 hardened air void analysis. And in this analysis, you take concrete, you wait for it to get hard, or you cut it out of a structure out of the field. You cut it and you polish it, okay? And then you look at it underneath a microscope. You come across this path. Okay? You come along here, and every single time this line hits a bubble, you start to count. It comes along, it hits another bubble, you start to count. You do that again and again and again. This is called a linear traverse analysis, and it takes about 3.5 hours for a human to do this with a microscope. The numbers that come out of this, though, can give you a lot of insights about the size and the spacing of your air void system, or what I like to call the quality of your air void system. And this is the type of numbers that you get out. Now, you're not actually measuring voids, you're measuring something called chords, which is a slice through a three-dimensional sphere, okay? But that's okay. This is an indication of smaller voids over here. This is an indication of larger voids over here, and I've plotted them based on frequency, or how often they occur. So everything underneath this curve totals to 100%. And we've got a green line and a blue line, and we can see the green line is a mixture with primarily small bubbles. Look at that. There's a big jump up or spike in the smaller chord sizes. And this blue line is mainly large bubbles, and look, there's a jump up or a spike in mainly these large air voids, okay? But again, both of these have about 6% air in their concrete, okay? So people usually don't like to look at graphs, especially engineers. I mean, we're great people. I'm an engineer, so I can say this. We're great people. We mean well, but we like numbers, okay? We just love numbers. And there is something that can take that curve I showed you on the previous page and turn it into a single number. And this is something called the spacing factor, developed by T.C. Powers in 1949. Okay? And what Powers did was something truly amazing for his time period. He took this idea of this three-dimensional bubble system, which he did not measure. He measured a slice through it. Okay? And he came up with a mathematical similarity of an equal-sized bubble, equally spaced inside the average volume of cement paste. Okay, there's a lot of averaging and equalizing and a little bit of hand waving that goes on some of this. But ultimately, this thing is called L bar, or the spacing factor. And this diagonal distance, okay, is twice the spacing factor. Okay? And it's ideally the maximum distance that a water molecule would have to travel on average to find a surface, okay, a void. You say, wow, I didn't understand any of that. That's okay. That's okay. It's fine if you didn't. What you need to know is the value that you need is 0.008 inches. And you want your value to be less than 0.008 inches. Okay? That's the magic number. So we can go back to these plots, the same plots I showed you before, and you can say this green line has a low spacing factor. You can say the blue line has a large spacing factor. All right? There you go. Let's look at more data. So here, now we've got air content down at the bottom. Okay? Now we have spacing factor on the y-axis, and we can see as the air content goes up, the spacing factor goes down. And look, here's the magic number, 0.008. And when you get about 5.5% air in your concrete, the world is a great place. If you get 5.5% or above, the world's a great place, and everyone's happy. Spacing factor is where it should be. You say, Tyler, I know. That's what we do right now. That's what our spec books tell us to do. Yeah, but guess what? This concrete mixture only has a single admixture in it, an air entrainer. That's exactly what Kliger investigated in 1952 when he developed his original recommendations, which are the basis for all air content specifications in the world. Okay? But now let's look at it. Let's add another admixture. Let's add another admixture that happens to produce larger bubbles. And now what we can see is that if we follow this same trend, down, that we need about 8.5% air in the concrete to make us have our magical spacing factor. 8.5% air. Wow. Wow, that's different. That's really different. So what happens on these larger air void systems if I don't have the right air content? Well, I'll show that to you. Usually people don't really care about spacing factor. Not really. We only use spacing factor because it's easy. What we care about is freeze-thaw durability. Okay? But ultimately, the goal of this plot, and I'll get to the freeze-thaw in just a second, the goal of this plot is to just point out that you cannot tell the size of the bubbles you're dealing with by looking at only the volume. It's impossible. You can't. If you go up here at 6% air, in one air void system, you're great, everyone's happy. Another air void system, people are not going to be happy, and I'll prove that to you right now. We've got two mixtures here, okay? The concrete is exactly the same, but the admixtures are a little bit different. And in mix A, look at this. This is the air volume down at the bottom, air volume. This is the performance in the ASTM C666 test, the rapid freeze-thaw test. And you want to be above 70% of this test. And some people will argue, well, should the number be 80? Should it be 70? Should it be 60? Well, we've picked 70. It's somewhere in the middle. And we can see here, as the air content goes up, you can see durability factor or performance in this rapid freeze-thaw test gets better. And look, all of a sudden, we're above the yes line, and everything is great. And look at this line. I need about 3% air to be happy with this mixture. 3% air in this concrete mixture. I don't mean to imply that works for all of them, obviously, but in this one it worked. And then let's look at mix B. It happens to have larger bubbles. And as the air content goes up and goes up, that you actually need something like 6.5 to 7% air in your concrete to get freeze-thaw durability. Okay, if you place it at 5%, which would be allowed by many specifications, you would not be getting freeze-thaw durability with this system. It would fail the freeze-thaw test. But look, if you're in the purple though, oh baby, you would be awesome. It would be amazing. Okay, that's the small bubbles, but with the large bubbles, it's not right. You say, well, how can this happen? How can this happen? Well, remember, all modern specifications are based on research done in 1952 by Paul Klieger, the Portland Cement Association, and he only looked at systems with single admixtures, air entrainers, because that's the only admixture that was available at the time. Here's more data. More data. Here's air content at the bottom. Here's spacing factor over on the y-axis. And now, if something is an open dot, that means it failed the freeze-thaw test. That means it had a durability factor greater than 70. And if it's a closed-in or filled dot, that means it had a durability factor. A durability factor greater than 70 is a filled dot. Durability factor lower than 70 is an open dot. My apologies. This is the failures, the open dots. The filled dots, that's the passing. Okay, and you can see here, if I get about 3.5% air in my concrete, everything is great. Everything is awesome. I'm getting freeze-thaw durability, but these are mixtures with only small bubbles on them. Let's look at this one. These are mixtures with large bubbles. And again, same thing applies. If it's an open data set, if it's an open data point, that means it failed the freeze-thaw test. And we can see we have many data points here. Many data points that are within air content specification volume ranges. And these two in particular, these two data points would meet any freeze-thaw specification in the world. Any in the world. Yet, they are failing the freeze-thaw test. So, in summary, we need to know the size of bubbles within our concrete. And the volume of air does not tell us anything about the bubble size. And although a hardened air void analysis can measure this, it's just not practical to run regularly. Okay? So we're going to talk today about something called the super air meter. We've taken a normal air meter and we've modified it so that it can hold higher pressures. We've also replaced the dial gauge with a digital one. And this digital gauge is really, really important. This is what the air meter looks like. Now first, this air meter has 6 clamps around the outside. 6 different clamps. And why does it have 6 clamps? Because it's going to go to higher pressures. Also, this air meter's got the digital gauge at the top. This digital gauge is so important. The gauge will tell you how to run the test. It gives the operators instructions on how to run the test. Then it watches them run the test. And it tells them, guess what? You ran this wrong. You didn't do it right. It's no good. Or thumbs up. You're doing great. Everything is great. And again, if they don't run it correctly, it voids the test, makes them dump the concrete out, tells them to run everything over again. Okay? And then it does all the calculations for them. And it gives something called the air volume, same number that we've had before, and there's something called the super air meter number, which I'll explain what that means coming up. And of course, we're at Oklahoma State, and at Oklahoma State we are Cowboys, and we are orange, and of course it is orange, just like us at Oklahoma State. Now, this test method is a provisional test method. This is you can find it at AASHTO TP118. And also, all the information about the super air meter you can find on this website, superairmeter.com. So let's talk about how it works, or how you run the test. There's a top chamber up here, and there's a bottom chamber down here. This is where just the air goes. This is where the concrete goes. This is where you consolidate the concrete, where you add water to the zone above the concrete, right? And then you go to start to run the test. Now on this plot, this is going to be time on the x-axis, and this is going to be pressure on the y-axis. And the top chamber is shown by this dashed line, and the bottom chamber is shown by this other dashed line. And the first thing you do is you pump the top chamber up to 14.5 psi. That's the same pressure we use now in a typical air meter. Then you hit the lever, you smack it with the mallet, and you get an equilibrium pressure. That's the green line. That is no different than what we're doing right now. And the super air meter, the test is no different. It's not run any different. And the super air meter will tell you the air volume that you have in your concrete right then and there. But usually, you would be done with an air test, but not with the super air meter. Not with the super air meter. With the super air meter, you leave the petcocks closed. Okay, you don't open them. You leave everything closed, and you pump the top pressure up, the top chamber up to 30 psi. You hit the lever again, you smack it with a mallet, and then you do it again. And now you pump it up to 45 psi. Again, you hit the lever, you smack it with a mallet, you get another equilibrium pressure, and you notice you've drawn a curve. And at this point, now you open the petcocks. You have to add water again to the bottom chamber. And there's videos online that show you how to run this on superairmeter.com, take you through step by step and show you how to do it. And then after you release the air in both the top pressure, in the top chamber and the bottom chamber, you do everything again. You fill it with water, you pump it up, you go through the same pressure steps. And you basically compare the first curve to the second curve. And believe it or not, those curves will not be the same. And I'll tell you why coming up, why they're not the same. But they are not the same. And the differences between these two curves will give you insight to the air void size and spacing inside your concrete. Okay? And this is how we calculate the SAM number. Okay? The numerical difference between the second curve and the first curve is how we calculate the SAM number. So how long does all this take? Well, if you have an inexperienced user, and I don't mean the first time the person picks up the air meter. I mean a person that's maybe done it a few times, but is maybe less than 50. They should be able to run the test in 10 minutes, okay, after they figure out how it all works. An experienced user can run the test with the pump that comes on it easily in 7 minutes. We do it all the time in my lab. We can do it under 7 minutes all the time. Now, if you have to go fast, if you need to go really fast, then you need to use something called the cape. And I'll explain what the cape is coming up. And an inexperienced user that's using the cape can run the test in about 7 minutes. But an experienced user, someone that really understands what they're doing, really knows all the tricks, is really going, they can run the test in about 4.5 minutes. So here's the cape. Okay, it's a regulator. It's a portable air tank, and these regulators have been pre-set up so that the green hose will spit out 14.5 psi. That's the first step on the super air meter test. The yellow hose will spit out 30 psi. That's the second step on the super air meter test. And the red hose will spit out 45 psi. That's the third step on the super air meter test. So this means that you don't have to really use the pump very much on top, or if at all. You would use these different hoses to help dial your pressure in. And it can make you go really, really fast if you have to go fast. So the super air meter gives you two numbers: the volume of air, the same number you've gotten before, and then something called the SAM number. And this cape is a portable air tank and regulators that can really help you run the test much, much, much faster. So why is the super air meter useful? What is it all about? Why is it useful? Well, let's show you some data. Now this is the number on the x-axis that comes out of the super air meter, the SAM number. And you can get it between 5 and 10 minutes, okay? And this is the spacing factor. This is the number that comes out of the hardened air void analysis. This is the number that T.C. Powers came up with, 1949. This is the test that even if you're really good, is going to take you 7 to 14 days to get the data for. And what we've done is we've plotted and shown the magic 008-inch spacing factor number. And then we've shown the recommended SAM number. Now, we found that a SAM number of 0.20 correlates very nicely with a spacing factor of 008. It, in a sense, separates out the data. What this means is that if your SAM number is greater than 0.20, then your spacing factor is greater than 008. That puts you in this quadrant. That's the no quadrant. That's the I'm not happy quadrant. If your SAM number is less than 0.20, then your spacing factor is less than 008. That's the yes quadrant. And this data falls in these two quadrants 92% of the time. That's pretty good. It's pretty good. And this is data from my lab. This is also data from field data from the state of Oklahoma, from about 60 different sites. And this is also from about 50 lab mixes done at FHWA Turner Fairbanks. Okay? So third party, they did everything. They did all the SAM testing. They did all the hardened air void analysis testing. 92% agreement. Now here's some data from Pennsylvania DOT. And this is really cool data. These folks got a super air meter. They had 3 different users. They went out and just started measuring. Okay? And they did all the SAM measurements. They did all the spacing factor measurements. And here's their data, plotted on the same type of axes. And again, there's an 83% agreement from the first quadrant to this quadrant over here, this lower left quadrant to this upper right quadrant. 83% agreement. That's pretty good. It's pretty good. And they did everything. It's 50 different field mixes. Now, these are from other members of my pool fund study. And this is from about 10 different state DOTs. This is over 100 different field mixes. And if we plot them in the typical 0.20 versus 008-inch lines, here's the yes quadrant, that's the no quadrant. There's a 68% agreement. That's still pretty good. Speaking of which, these are some people that just picked up the super air meter for the very first time. Okay? But what it suggests is that if you slid the limit to 0.25, you'd say, well, why would you do that? Why would you slide the limit? Well, I'll show you a good reason coming up, okay? And I'm not saying you should do this, but as more data comes in, as more observations come in from a wider audience, I think it's reasonable to think that a technology that's being established for the first time may evolve a little bit. And this may be a little bit of that evolution, is that this data is showing that, you know what, if you moved it over to 0.25, you got a 79% agreement, which is a little bit better. But don't worry, I'll talk more about that coming up. So a SAM number of 0.20 correlated well with a spacing factor of 008 for over 350 different lab and field mixtures completed by 13 different states. And the field mixes from state DOT suggest that a SAM number of 0.25 may have a better correlation to a spacing factor of 0.008. Okay, now let's move into freeze-thaw durability. Okay, for freeze-thaw durability, we've got the SAM number down here on the x-axis. We've got the durability factor on the y-axis. Remember, this is the test, SAM number. This is the test. It takes 5 to 10 minutes that you get into the fresh concrete. Durability factor, this is the one from the ASTM C666 test. This test takes 3.5 months to run. That's a long time. But again, if we use the 0.20 limit right here, this is the yes quadrant, this is the no quadrant, there's an 80% agreement. But look. There's several of these mixes that go past this 0.20 to a 0.25. If we move this limit to 0.25, we get an 89% agreement between this upper left quadrant and the lower right quadrant. You'd say, well, how did you know? Well, remember, we established the 0.20 limit based on a spacing factor of 0.008. That was the original work that we did. And I don't regret any of it. But we do spacing factor measurements to find out more information about freeze-thaw durability. I mean, freeze-thaw durability is the real indicator of what we care about. And here's a whole lot of data that's showing us that, guess what? For freeze-thaw durability, a little bit higher SAM number. And actually, if you go back, I mean, I don't think that's unreasonable. People for a long time have seen that sometimes a spacing factor of 0.008, although conservative, can sometimes be adjusted a little bit. Now let's talk about this mix. Here we go. If we compare durability factor, this is the test, this is the results in the ASTM C666 test. Same stuff I showed you before. But instead of using SAM number, now we're using spacing factor. And again, there's the magic 0.008 inch number. And here's, if you look at the upper left or the lower right quadrant, there's a 69% agreement. What does that mean? That means the SAM number has a better agreement. That's the stuff I showed you before. 80 to 89% agreement. This is about a 69% agreement. SAM number is showing a better agreement to freeze-thaw durability than just a spacing factor. So the SAM number 0.20 correlates better to rapid freeze-thaw durability than a spacing factor of 0.008. A SAM number of 0.25 shows a better correlation to the freeze-thaw durability limit as well. So this is the graph I showed you earlier. This is the graph where we had air content at the bottom. We have durability factor, freeze-thaw performance, and we have these two data sets. And it's really hard by just using air volume to tell these two apart. For example, at 5% air, I cannot tell whether I'm going to have a freeze-thaw durable or non-freeze-thaw durable concrete mixture. But if I use the SAM number instead, okay, this is the number from the super air meter, you can. All the data is leveled. All the data is on top of one another. You can determine the difference between a good air void quality or good freeze-thaw performance versus bad freeze-thaw performance by using the SAM number. Okay? So why is this useful? The SAM number can tell us about the quality, the size and the spacing of our air void system before the concrete gets hard. It can tell us about freeze-thaw durability of our air void system. That is big time. It can warn us about air void stability problems during the mixture design process. We can know whether we're going to have big bubbles or not when we're putting all of our ingredients together. That is big time. This can give us critical information that was almost impossible to get in the past. It can help you when you design mixtures in the lab, when you place mixtures in the field, when you're trial batching in the field, when you're troubleshooting field problems, when you're measuring variation in your materials. Okay? This is a very insightful thing. Now, I've had people call me up. They've heard me talk about this. And they said, Tyler, and they'd say, hey, I've got a paving job. Perfect example. Recently in Oregon, I got a call. Said, I got this paving job. I'm trying to help the contractor out. The air void systems are all over the place. What's going on? What's going on? Can the super air meter help me figure this out? And I said, yes, that is exactly what the super air meter is good for. They got it, and within 2 days, they had that the sand gradation had changed just a little bit, had gotten coarser, and that they were using a new mid-range admixture that they didn't realize. And when they switched back to the old one, they didn't have any problems anymore. Okay? And when they heard that, when the contractor saw that, they wanted a super air meter, their friends wanted a super air meter, the admixture people wanted a super air meter. There are huge benefits. People are excited when they can see the ability of how this can help them make better, more consistent concrete. So how would I do this? This is a brand new tool. Brand new tool. Okay, this is very cool. This is a plot that you can make out of the two parameters that come out of the super air meter. The x-axis is your air content, or your air volume, and the y-axis is your sand number. Remember, these are the two things that come out of the super air meter. And mixtures that have large air voids plot near the top red line. And mixtures with smaller air voids plot near the bottom line. And don't think that you're going to be on one line or the other. There's like a whole continuum here. Okay? But based on about 600 different concrete mixtures with large air voids plot near this top line, mixtures with small air voids plot near this bottom line, or possibly below. And this means that you could plot for your concrete mixture a single point and you would know immediately what was going on. So for example, I have two mixtures. This is where everything was going great for mixture one. This is real field data, by the way. Everything was going great at a mixture number one. They were getting the sand number of 0.22, an air content of 5%, and all of a sudden they got a sand number of 0.40 and an air content of 6%. And they said, what? What's going on? Because if I plot those two data points on this line, mix number one, everything was great. Mix number one, I had small bubbles, and they saw it for themselves. They saw that their air void systems weren't stable anymore. Okay? They were plotting near the second line. Also, the sand number was pretty high. Okay, really high. And it wouldn't necessarily be freeze-thaw durable. It would immediately help them go back and troubleshoot what was going on, what was happening. And this immediate feedback is exactly what our industry needs. Okay? This is simple and easy and fast. And it's in 5 to 10 minutes, you get this information from your concrete in the field and you can make real-time adjustments. This is helpful. So here's some data from Pennsylvania DOT. And look at this. Look at this. Think how valuable this is. They knew all these mixtures immediately would have large air voids. They knew all these mixtures had small air voids and these were somewhere in the middle. This is crazy valuable. These are all data sets from 11 or 10 different state DOTs. And again, they could find out immediately if they had small air voids or possibly really small air voids, or they were having coarse air voids or possibly really large air voids. Again, that immediate feedback is really, really helpful and important. So by plotting your data on the SAM curve, you can immediately tell if your air void system is made up of large or small bubbles. And this immediate feedback can be used to troubleshoot field issues and give you feedback on your concrete mixture design almost instantly. So how does this super air meter work? How does it work? What's it all about? Well, to show you what it's about, I'm going to take these bottles that are about 3 inches tall, about 2 inches wide, and about 3/4 of an inch deep. And the cool thing is that they're optically clear. I can see through them. Okay? And we're going to fill them up full of air-trained cement paste. Okay? And we're going to put some water on the top of them, tilt them over on their side, and this is this is the paste, and over time, bubbles are going to rise up and get caught on the bottom of the glass. And so the data I'm about to show you is not the air void system inside the cement paste. It is not. But it are the air bubbles that were in the cement paste that rose up and that were on the surface and we're able to watch with a stereo microscope, an optical microscope. We have an air pump over here, and we can pressurize it and simulate an air test. So here we go. Atmospheric pressure. These are the bubbles, all the bubbles around here. Let's watch the test. Here's one pressure. Here's another pressure. Notice some of these bubbles don't look happy. They look a little different. There's some shifting as well. Here's the third pressure. Some of these bubbles don't look spherical anymore. Okay. Go to the fourth pressure. Man, doesn't there seem like there's a lot less bubbles? Let's watch these two bubbles down here. Watch these. Fourth pressure. Gone. Disappeared. Not there anymore. Those bubbles are dissolving. They're dissolving into the solution. There's the sixth pressure. There's the seventh pressure. Wow. The bubbles that are sticking around are these large bubbles. Now watch. I'm going to take it back to atmospheric pressure. Look at that. Some of the bubbles came back, but not all of them. This is what it used to look like. This is what it looked like after the pressure steps. Wow. What's going on? What's happening? As the pressure increases, the small bubbles dissolve into the surrounding solution. These bubbles do not immediately come back when you decrease the pressure. Notice that the bubbles in this experiment are not close to one another. That's a big time point. I'm going to come back to that coming up, but the bubbles aren't close. They're kind of far apart. So what's going on? Well, there's an equation called the Laplace-Young equation, and it's stated right here. And it basically says that the pressure P inside a bubble is a function of the fluid pressure around the bubble, the diameter of the bubble, and the surface tension of the bubble wall. Therefore, as the diameter of the bubble gets smaller and smaller and smaller, the pressure in the bubble is going to get larger. It's inversely proportional, right? So it shows right there. And here's a plot of that. This just shows that if I have a larger bubble, 300 microns or so, they're going to be much closer to atmospheric pressure than if I have a smaller bubble. They're going to be much, much larger for a given surface tension. So why would bubbles dissolve? Okay, so that might explain that Henry's law on the last one might explain why the bubbles, smaller bubbles are at a higher pressure than the larger bubbles. But why would bubbles dissolve? Why would they go away? Well, there's a phenomena called Henry's law. And Henry's law says that at a given pressure, that a certain amount of gas will dissolve in a liquid. Henry's law is super simple. It just says there's a constant for a certain gas and a certain liquid combination. And it says that at a given pressure, there's a certain amount of that gas that's dissolved in that liquid. So at a higher pressure, more of that gas will dissolve in the liquid. That's why smaller bubbles, higher pressure, those bubbles are going to be the first to dissolve inside the liquid. So as you increase the pressure, air will dissolve into the surrounding solution, and because the smaller bubbles are at a higher pressure, they will dissolve before the larger bubbles. So let's do some more experiments. We're going to do some additional experiments where we actually track how individual bubbles change every 5 psi. We're going to do that from atmospheric pressure up until 35 psi. And we're going to look at two different situations. One, when the bubbles have a high spacing factor, the bubbles are far apart from one another. And then two, when bubbles have a low spacing factor or bubbles are close together. Now first, I'm going to give you an overview of everything. So we got the high spacing factor bubbles far apart here on the left. We're going to take them up to 35 psi. I didn't show you the interim steps. Just took it up to 35 psi. Then returned everything back to atmospheric pressure. And notice some of the bubbles come back, but not all of them. Now let's look at the low spacing factor. Look at these bubbles, closely spaced bubbles. As you increase the pressure, some bubbles dissolve, but a lot of them don't. But when I decrease the pressure, a large number of the bubbles stick around. But the important point about this slide is that the bubbles with low spacing factor, bubbles close together, have a totally different performance than bubbles are far apart. These mixtures are the same. They have the same dosage of air and trainer. Actually, dosage of air and trainer is a little bit different on the one on the right. This just happens to be where we looked at a cluster of bubbles. This just happens to be where we looked at bubbles far apart. Totally different performance. Now let's show it graphically. I'm showing applied pressure at the bottom. So here's atmospheric pressure. Here's 5, 10, 15, all the way up to 35, then back to atmospheric pressure. And this is the air bubble diameter that we measured. Notice here that both of these red are the high spacing factor bubbles, the bubbles far apart. The blue are the low spacing factor bubbles close together. These bubbles are both very similar in size originally, but the high spacing factor bubbles behave similarly up to about 10 psi. But about 15 psi, they start to perform very differently. 20 psi, there's a major difference. But by 25 psi, this X means the bubble dissolved. But look at the blue one. It kept going, and guess what? When you decrease the pressure, the bubble comes back. And it's very similar in size, or close to being the same size as what it originally was. This means that bubbles in a high spacing factor system, bubbles far apart, almost entirely dissolve when you pressurize them. Not totally, but a lot of them dissolve and do not come back. But the bubbles in the low spacing factor system, bubbles close together, do not dissolve as much. But why does this happen? As the bubbles dissolve, they increase the local concentration of dissolved air. So closely spaced bubbles are going to cause a localized saturation of air around them. And this is going to cause the bubbles to no longer dissolve in the solution from the increased pressures. The bubbles are far apart, then there will be no localized saturation, and the bubbles will continue to dissolve with increases in fluid pressure. So I'm going to talk about this. I'm trying to get really practical for a second on why we do the test the way we do it. Pressure step number 1 is our first pressure cycle. Pressure step number 2 is our second pressure cycle. And remember, I told you earlier, we compare the two pressure cycles to determine the quality of the air void system inside our concrete, or the SAM number. If you have a high spacing factor, bubbles are far apart, then when pressure step number 1 happens, it's going to cause your bubbles to dissolve. Then, when we apply pressure step number 2, when you punch it the second time, there's going to be a large difference in how the concrete responds to pressure. That's important. Big difference between pressure step number 1 and number 2, because the bubbles are far apart, because the bubbles dissolve, so the bubbles are not there anymore. When you go to push on them the second time with pressure step number 2, that will cause you to have a high SAM number. If you have a low spacing factor, bubbles close together, then pressure step number 1 will not dissolve very many bubbles. So when you apply pressure step number 2, there's going to be a small difference because the bubbles are still there. When you go and you punch it the second time, a lot of those bubbles are still sticking around. So it's going to behave similarly, not exactly the same, but similarly to how it did the first time. And this is going to cause you to have a low SAM number. So we've used empirical testing basically to relate all of this to the SAM number, to the spacing factor, to the freeze-thaw durability of the concrete. And that is how we use the SAM number to predict freeze-thaw durability. So how variable is this method? We've done, this is still ongoing, but we've done multiple operator comparison of mixtures at Oklahoma State and all, with 4 different operators at once, and also in Chicago at one of our training sessions with up to 6 operators at once. And here's what the data looks like. Here's the coefficient of variation. And I've got it reported from what we have in our lab versus to what we measured in the workshop. And they're pretty similar to one another. If you compare the coefficient of variation for what's reported by ASTM C457 for the spacing factor, okay, that's a coefficient of variation of 20.1%. And if you look at the coefficient of variation for what's reported for a durability factor, okay, for a durability factor of about 75, and using method B, you get a coefficient of variation of about 22.7%. They're all very, very similar to one another. Yet, the super air meters only take 10 minutes versus 7 days or 3.5 months. The super air meters have an 80% agreement with the freeze-thaw test, okay, and only a 69% agreement with the spacing factor. So, what's going on here? The variability of the SAM is similar to the variability in the hardened air void analysis and the rapid freeze-thaw testing, and the results from the SAM correlate with the rapid freeze-thaw and the spacing factor. That's good. But the SAM can be run on fresh concrete in 10 minutes. There's a lot of advantages there, a lot of benefits. And I don't think personally that it's a coincidence that the variability is so similar between these three methods. Each test is designed to investigate the air void quality of the concrete, at least as long as you have good aggregates and you have a good water to cement ratio. And air void distribution, air void quality, air void spacing, air void size may be more variable than other properties that we're used to dealing with, such as compressive strength. Okay, compressive strength has got about a coefficient variation of around 10%. Okay, this one's got a higher one, but it may be that this parameter in concrete is just a little bit more variable. So you have to be a little bit careful about how you use it, but that's okay. I'll talk about that coming up. The following states, as of this day in November 2016, have super air meters, okay? And the number in parentheses is the number of super air meters that they have. And the states that are in gold are the states that have started to specify and train on super air meters. And this is also being used in Poland and in Canada and in England, so 4 different countries outside the United States. So how do you specify the super air meter? How are people doing this? And I'm going to present 2 procedures right now, and this is evolving and ongoing. And one procedure is a very prescriptive specification. And this is a little different. This is a little bit different approach. But during the mixture design stage, you run a trial batch. That's not that different. But you force people to use a low air content. You force them to have an air content to be less than 5%. You say, why would you do that, Tyler? Well, you're forcing them to have a lower air volume. And you're making sure that at that time they use a lower air volume, that they get a SAM number of 0.25. So what you're doing is you're checking, I'm going to make sure I'm on the bottom end of the spec, and I'm going to make sure my SAM number is pretty good. Hey, and you can change these numbers to be whatever you want. But as long as my SAM number is less than 0.25 and I'm near the bottom of my spec, I'm happy and I'm good. And being near the bottom of the spec is very important. But now you got to make sure you get that in practice. Well, you can, first of all, use typical air meters, typical air specifications in practice, but you should still roll out the super air meter once a day, and you should validate that your air is less than 0.25, your SAM number is less than 0.25, and your air volume is greater than 4% once a day or every 800 yards, or you fill in the blank. 1,500 yards, 1,000 yards, whatever one you like, okay? Here's a performance specification. In this one, they don't tell people how to do things. They just say, make concrete, I will measure concrete, I'm not going to use a typical air meter, I'm going to use a super air meter, and if my SAM number is below some number, I think 0.17 is a good number, you're going to get a bonus. If you're between 0.17 and 0.25, you get full pay. If you're between 0.25 and 0.30, you get a deduct. If you're greater than 0.30, you reject the concrete. Now that shouldn't be startling. We reject concrete now sometimes, so that's not totally out of the ordinary. But you should give people a bonus if they do things well. You should at least give them full pay if they do things good enough. And you shouldn't kill them right off the bat. You should have a warning sign or a deduct. Now, if people will design their concrete mixtures in the lab at about a SAM number of 0.17 or 0.18, based on the standard deviations and the coefficient variations, in a 90% confidence interval, you will not have any deducts at all, okay? As long as everything's consistent. And again, your air content must always be above 4%. That's just a good idea to have. So what do I do if my SAM number is too high? People ask me this sometimes. If I have a truck that shows up on the job site and my SAM number is too high, about the only thing you can do is add air. As air goes up, SAM number will go down. Okay? Only thing you can do is add more air, and if you've done some trial batching beforehand, you should know about what air content you need to get get a certain SAM number. Now, let's say it's not. Let's say you're consistently producing high SAM numbers. Well, you can modify your mixture proportions. That's probably the number one thing you can do. You can really start to look at your admixture combinations. You can look at your admixture cement combinations. And this is something that's going to need to be done. This is something that's going to be, people are going to want to pay much more attention to. Okay? And this is going to be a change, something that we're going to have to adopt to. It's going to be different. Also, you might want to look at your mixing and your batching operations. Is there something going on that's maybe why I have a SAM number that's too high? But ladies and gentlemen, I'm going to need your help to do all this. Because what I'm asking you to do here is do something very different. We are taking a technology, okay, from, do you know that Klein and Walker developed the air meter in 1946 at NRMCA? 1946. It's 70 years ago. This is a horse and buggy technology. We're taking it into a totally different direction. We're taking it into the equivalent of an internal combustion engine. Changing from a horse and buggy to an internal combustion engine is not easy. It's going to take a lot of adaptation. But think about the benefits. Think about how much our industry had to change to go from a horse and buggy to an internal combustion engine, but think of how great it is today. Think of all the great things that have happened because we did it. The same thing's going to happen with the super air meter. It's going to take a while to adopt. Not everyone's going to want to adopt, but those that do and those that will reap the benefits. I promise you, there's a lot of benefits of the super air meter. So I need your help. Taking the industry from a horse and buggy to an internal combustion engine is not easy. I need you to try the SAM. I need you to ask questions. I need you to give me suggestions. I'm about to give you my email address. About to give you my website. I want you to email me. I want you to tell me what you think. I need to share what you learn from here with other people. I need you to help others become knowledgeable about the super air meter and the secrets of freeze-thaw durability. So we're going to go back to that big picture. We're going to go back to what I know in my core, and I think you will too if you ask yourself this at your heart. We need our infrastructure to last as long as humanly possible with little to no maintenance, and we need our materials to last as long, be long-lasting, to remain relevant. If they're not, we will find another way. And we need tools, though, to help us achieve this economically and without impacting our productivity. And I think the super air meter is a great way to do this. So in conclusion, large bubbles are your enemy. Air volume does not tell you about bubble size, but the SAM can measure the volume and size distribution of the bubbles in fresh concrete, and this is helpful for making your air more consistent and ensuring freeze-thaw durability. A SAM number of 0.20 seemed to correspond to the spacing factor of 0.008, and over 90% of the lab and field data is correctly separated with this limit. The SAM number correlates with an ASTM C666 testing, and the SAM has been investigated by a number of others, and all have found similar correlations. So, if you have any questions, there's my email address, there's my website where you can find out other things that I'm up to, and there is the Super Air Meter website. Thank you so much for being here with me today. I really appreciate it. Go Concrete.